Hello everyone. Welcome to the day 18 of the Machine Learning Teach by Doing project. In this particular lecture, we will put all the pieces of the puzzle together for logistic regression. Up till now, we have looked at defining the sigmoid hypothesis, defining the cross entropy loss function, and in the last lecture, we also looked at gradient descent and how it works. We now have all the toolkit which is needed to implement the entire logistic regression from start to end from scratch. When you go for coding interviews or machine learning job interviews, there is a question which interviewers typically like to ask, where they ask you to implement the entire logistic regression from scratch. And many candidates are not able to do it because their foundations of logistic regression are not clear. They know how to just use the logistic regression command which is provided by Python scikit-learn package, but they don't know the implementation behind it, nor do they know the mathematics behind it. Today we will not just learn the mathematics, but we will learn the coding also. We will do both of these things so that whenever someone asks you this question, you are comfortable with the foundations from scratch entirely, and you will also able to code the logistic regression from scratch in Python. This lecture will assume some basic knowledge of matrices and some very basic knowledge of linear algebra. And when I come to that part, I'll also let you know that what all knowledge you need. And if you don't have that, you might need to revise your concepts. But it comes up at very small portions, so do not worry about it. You can still follow through with the entire lecture. So, to those who are joining this for the first time, here is the problem at hand. We have on the x-axis, let's say we are measuring the whisker length of the particular animal, and in the on the y-axis we have ear flappiness index. So let's say we have two types of animals, dogs and cats, and we collect data for both of them. So for dogs, their ear flappiness will typically be higher, and their whisker length would be lower, but for cats they would lie hopefully somewhere here. The goal of this particular exercise, or the goal of logistic regression, is to find the best possible hypothesis or find the best linear classifier which separates these two types of data sets. The linear classifier itself is given by three variables: theta 1, theta 2, and theta naught. So it's like theta 1 x1 plus theta 2 x2 plus theta naught, and this is x1 and this is x2. In linear algebra setting, this is also sometimes referred to as theta transpose x plus theta naught, where theta transpose is just theta 1, theta 2, and x1 is just x1, x2 plus theta naught. So the ultimate goal is to find the optimal theta 1, theta 2, and theta naught, which best separate these two types of data sets. Earlier, we tried the perceptron approach and we tried the random linear classifier approach. But for logistic regression, or for most of the machine learning algorithms which we'll learn henceforth, they use something called ML as optimization. So essentially, we will be using an optimization approach here, which we also motivated 2 to 3 lectures earlier. What this means is that we will define a loss function, and then we will try to find out the parameters theta 1, theta 2, and theta naught which minimize that loss function. That is what we will be doing. So let's say the objective function is j of theta, which is 1 by n, where n is the number of data points and L is the loss function. And usually the loss function is the difference between the guess and the actual value. Uh, when we move to advanced machine learning algorithms, we also have a regularization term here. But for the sake of simplicity, I will not be considering the regularization term in this particular tutorial, and we will just look at the loss function. So the goal is to find that particular theta star which minimizes j, or which in turn minimizes this particular loss function. The guess is made by our hypothesis class, and we looked at this hypothesis, which is also called as the sigmoid hypothesis. So let us come to these two functions which we have already learnt in the previous class. L is the cross entropy loss for logistic regression, and it is defined as follows. Let me write the definitions in pink color. So L is the difference between the guess, which is the hypothesis, h of theta, and y, which is the actual label, and that is given by negative of y multiplied by log of h theta plus 1 minus y multiplied by log of 1 minus h. This is the cross entropy loss function which we defined in the two lectures back. Now you must be thinking, what is the hypothesis? And the hypothesis class also we have defined in one of the previous lectures. And h of theta is the sigmoid function. H of theta is the sigmoid function which is given by 1 upon 1 plus e raised to minus theta transpose x. For this derivative right now, or for this derivation which I am going to do, I am not going to be using theta naught because it will just make things a bit more complex. But in the hands-on demonstration, which is the part 2 of this lecture, I'll show you exactly how we can deal with theta naught. Okay, so now we have the loss function L. We know the formula for the loss function, and we know the formula for the hypothesis class. So let us put both L as well as H in J and see what this function actually looks like. So now when I put L and H in J of theta, it looks like this. J of theta is equal to minus 1 by n sigma I goes from 1 to n yi log of sigma of theta transpose xi plus 1 minus yi into log of 1 minus sigma theta transpose xi. Let me mark this objective function or the loss function which I want to minimize. What I have done is that I have just taken this loss function, the cross entropy loss, and the hypothesis and plugged it here. The h theta I replaced with this sigmoid function. So it turns out that this is our loss function which we need to minimize. So this is the step one. We want to find theta star which minimizes j. You see how we have converted the logistic loss into an optimization problem. Now it's no longer a machine learning problem. Now it comes down to mathematics. That's it. That's why people tell you that to master machine learning, you need to master optimization and statistics. Because when you formulate a problem as an optimization problem, it looks something like this. And now you want to find theta star which minimizes j. So this is step one. Now let us look at step number 2, which we have already prepared for in our toolkit. It is implementing gradient descent. And remember what gradient descent was. Gradient descent updates the theta value. So it starts with some theta which we don't know, and then it updates it based on the step size and the gradient of the function at that particular theta. So this is the step size, and this is the gradient of that function at that particular theta. So in order to implement gradient descent, we will need to find the gradient of this function j, which we do not know at the moment. And I'm not going to go into the mathematical details of this derivative calculation, but it turns out that so we need to find this quantity, right? dj theta, which is the derivative uh, with respect to theta. And it turns out that this particular quantity is actually a very simple expression. It turns out that this quantity is just sigma I goes from 1 to n, the sigmoid function theta transpose xi minus yi multiplied by, so it turns out that this particular gradient, uh, it looks like to take the derivative of this function with respect to one particular theta, it would be a bit complex, right? But many things cancel out when you do this particular derivation. You can try it out for yourself for those who are mathematically inclined. For those who are not, it's completely fine. It turns out that the derivative with respect to theta of this loss function has a very simple meaning. So this particular quantity is just the model prediction that my ith data point xi belongs to class 1, and this is the true label. So it actually turns out that the derivative is just governed by the difference between the model prediction and the true label. Now remember that here we have to take the derivative with respect to every single theta value. Based on the number of features which we have, the theta will be having those many values. So in our case, we are taking two features, right? Whisker length and ear flappiness index. So theta will be just equal to theta 1 and theta 2. But if we have 5 features or 10 features, then this vector length will just keep on increasing. And when we calculate this derivative, we have to do that for every single theta value. And in the gradient descent, every single theta will be optimized. So every single theta will be updated. So this is the calculation of the gradient. And then that's it. The final step, which is step number 3, is that you just start out with some theta. So step 3 is like already I have mentioned here, but incorporating the gradient which we found out, alpha times theta by gradient of the loss function with that particular theta. That's it. So step 3 just states that let's say if you have two features, you start out with some values for both of those features, then you find the gradient of the loss function with that particular theta, and then you keep on updating those two features. Um, you might take 10 iterations, 20 iterations, 50 iterations. You have to figure that out on your own. But this is the algorithm for how we are going to do the logistic regression function. Remember, first we defined the loss function here, which we have to optimize. So this turns into an optimization problem. Essentially, we need to find that theta star which minimizes j. Now, whenever someone gives you such kind of a problem, the first thing you need to remember is that you need to find the gradient, because to use gradient descent, you need the gradient of that function. And here we are going to find the gradient with respect to the number of features which we have, because the length of the theta vector which will be based on the number of features which we have. If we have two features like the whisker length and ear flappiness index, theta will be a vector of two quantities, and both of those quantities need to be updated. So we need to find derivative with respect to both of those quantities. And this derivative, it turns out that if you plan to differentiate this with theta, you might think it's very complicated, but it turns out that the derivative actually has a very simplified expression which looks something like this, and it just depends on the difference between the model prediction and the true label. Once you have the derivative, then it's done. Then you just have to update the theta based on the derivative, and you also have to define a step size along the way, which you have to fix at the start. So this is how the gradient descent procedure and the optimization procedure for the logistic regression looks like. One thing which I immediately want to mention, and that also involves a bit of matrices, and I'm going to write this thing in orange color, is that if you know about matrices, right, or rather, I will say matrices, and if you know about linear algebra, it just makes our life very easy. Let me tell you why it makes our life very easy. So it turns out that if you know about matrices and if you can represent these quantities in terms of matrices, then you don't even need to find the summation every single time. There is a very simplified expression for the gradient. So first of all, in matrix form, let me write how the different quantities look like. So this is the normal form, which is the, I would say this is the vectorized form, and this is the matrix form. Okay. So first thing, theta transpose xi. This thing which I've written here. When you just write in terms of vector form, you need to take the summation because you need to find it for every single input vector x. But in the matrix form, this quantity just looks like x into theta. That's it. Uh, there is, I'm not saying this is equal to this, but I'm just saying that if you translate it into matrix format, it looks like this. And I will come to the detailed explanation of how this quantity can be used. And second quantity is in the gradient itself. You will notice that there is one more term, this minus yi. This translates to just sigma of x theta minus y, and y here is also the vector of the true labels, and this whole quantity just translates to this 1 by n x transpose sigma x theta minus y. You don't even have to worry about the summations. If you can represent the input vector, if you can represent the input in this kind of a format in the matrix, if you represent the input as a matrix x, uh, and if you represent this y, which is the true values, as a vector, then the gradient is just given by this. So it turns out that in a matrix format or in a matrix representation, uh, the gradient descent or the updates of theta turn out to look like something like this. So theta I plus 1 is equal to theta I minus alpha times 1 by n x transpose sigma x theta minus y. That's it. No need to worry about taking the summations when you find the derivative. It's just this simple expression. One thing to remember here is that so whenever someone gives you data for logistic regression, you first need to convert x into a matrix, and you need to convert y into a vector of true labels, and then you just use this gradient descent formula to keep on updating the theta values. Don't worry if you found this matrix part a bit complicated. I will be demonstrating to you a hands-on activity where we will calculate all of these quantities for a data set, and I will show you how to update theta and how to eventually find the best theta also. For now, I just want you to remember that when machine learning practitioners actually implement these algorithms, no one thinks in terms of summations and individual quantities. Everyone thinks about these values in terms of vectors because it's much easier to, sorry, everyone thinks about this in terms of matrices because it's much easier to handle matrices. So this gradient descent, if you can write this vectorized representation, it's no problem, but you can see the matrix representation is much cleaner to write, and it's also much easier to execute hands-on examples from scratch. That's why people say you have to learn linear algebra when you learn machine learning. Maybe I'll also update linear algebra tutorials. But for now, all I want to say is you don't need to master linear algebra. You just need to know this matrix formula right now. So don't be scared up till this point. Just keep this in mind. Make notes and write this note down. Now we will look at a hands-on example where all of these things will be clarified for you. I could have just left the lecture here, but then I realized that it would not. This mathematics is good, but you need to tie it with some practical demonstration so that as students you do not forget what we have learned over here. So now let us move to part 2 of this lecture, where we will be looking at a hands-on demonstration. Uh, Here we will be looking at a hands-on demo, and then in part 3 we will also be looking at a Python code. So in this hands-on demo we will implement the entire logistic regression from scratch. And if you do this yourself on a piece of paper, you will be so confident when you give interviews, because not many candidates would have implemented this from scratch like how we are going to do. So again, this is the whisker length, and this is the ear Philippines index. Okay. In this data set, what I'm going to do is I'm going to take 3 points for dogs, and this will be my negative data set, which means it will be the true label for this will be 0. True label for these will be 0. And then for cats, I'm going to take these 3 points over here, which is my positive class, and the true label here, the true label here is going to be 1. Okay. So let me write down these points here, because we are going to do a mathematical demonstration here. So we need to see the points. So my negative class, which is my dog, has 3 points, and they will be 1 comma 5, 2 comma 6, and 3 comma 7. And my positive class, which will be my cats, this will also have 3 points, 2 comma 1, 3 comma 2, and 4 comma 4. Okay. So let me just highlight this in a pink color. These are our data points, and this can be anything. When you go to an interview or when you think of a different question, the x and y labels can be anything, but the underlying principle remains the same. If you want to visualize this in VS Code, I have plotted this initial data for you. This is how it looks like. If you see the red crosses, those are negative dogs data, and if you see the blue dots, those are the positive cat data. And the points which have been marked here, its coordinates I have already given over here right now. Before we move further, I want to remember I mentioned to you about theta naught and what to do about theta naught. So I'm going to teach you about an augmentation trick right now. Augmentation trick, so that we can take care of theta naught in a good manner. So remember that in a two dimensions, there are two quantities. There is theta, which is theta 1, theta 2, and theta naught. So the classifier looks like theta 1 x1 plus theta 2 x2 plus theta naught is equal to 0. Now remember that what should I do if I want to get rid of theta naught? So for example, we always calculate this. So this quantity, right, what I have written over here, can also be written as theta transpose x plus theta naught, correct? And now what I want to do is replace a theta with a theta star, so that there is no need for theta naught. So somehow I want to augment things so that both of these will lead to the same answer. Let me take one example x and show you what I mean. So let's say, so theta transpose will be theta 1 theta 2, and if I take x to be 1 and 5 plus theta naught, this will be is equal to theta 1 plus 5 theta 2 plus theta naught, correct? Now the augmentation trick which I am going to do is that I am going to augment x by adding 1 to it. So instead of 1 and 5, I will also add 1, 5 and 1. This is that augmented value. And theta star will be equal to theta 1, theta 2 and theta naught. So I will incorporate theta naught within theta star itself. Now let us try multiplying these two quantities. If you multiply this vector by this vector, you will get theta 1 plus 5 theta 2 plus theta naught. You see, we get exactly the same answer. So what is done in the augmentation trick is that first thing which is done is that you integrate theta not into theta itself. So in the rest of the calculations, when I'm going to say theta, it means it also includes theta naught. And what we are going to do is that we are going to augment all of these points by adding 1. So we will add another value of 1 at the end of all of these points. This reason is because we don't want to. So for all these mathematical equations to hold, here we did not take into account theta naught, right? So this is just a trick which we do so that all those mathematical equations would still hold. So this is the first thing which I wanted to show you, the augmentation trick. Second thing, remember what I told you, that whenever someone gives you a problem for implementing logistic regression from scratch, we need to convert the input into a matrix. So convert input data into a matrix. What is our input data? We have 6 points as input, and they are augmented now by adding 1. So this is how my augmented matrix X is going to look like. Uh, the first column is just 1 for the 6 points, because this is the augmentation we talked about. And then I write my points. These are my 6 points. It's just simple. What we have done is that, see here, let's say we take this point 2 and 1, right? It's just written 2, 1, and we add 1 value as the augmentation. Then 3, 2, and 1. So 3, 2, and 1. Then 4, 4, and 1. Then 1, 5, 2, 6, and 3, 7. So basically, I've just taken all of my points and augmented it over here. So these top 3 points, these 3 points are my positive class, and these bottom 3 points are my negative class. One more thing which we need to do whenever someone gives you a logistic regression problem is to convert the labels into a vector. So I am going to call this capital Y, and corresponding to these I am just going to write the label. So the positive class will have labels 1 and the negative class will have label 0. That's it. So this is my input matrix. So this is my input matrix, and this is my true label vector. This is exactly what we discussed when we wrote this matrix representation. We saw that we need the matrix of inputs and we need the vector of true labels. So now we have obtained this. We have the capital X and we have the capital Y. Now actually look at this particular formula to update theta. You have every single thing which you need to update theta. you have capital X, you have capital Y, which is the vector of true labels. You know what the sigmoid function is. So what are we waiting for? Let's get started with the first iteration. Of course, I'm not going to do all the iterations here, but I'm just going to show you one iteration so that you get understanding of how to exactly proceed with the iterations. So iteration number one. So let us start with theta as 0, 0, 0. Remember that this third value is now equal to my theta naught. Remember what I mentioned in this trick, that I have integrated theta naught into the vector theta itself. So we start out with a random guess of theta, which is 0, 0, and 0. And now let me write this formula again. So my theta 2, which is my augmented theta, will be theta 1 minus alpha times 1 by n x transpose sigma x theta minus y, correct? So let us start evaluating these quantities step by step. First, I am going to evaluate x into theta. So this I have written as number 1 over here. Now you will see how easy it is to do matrix multiplication. So x into theta, and x I have already written over here. See, and theta is 0, 0, 0 initially. So x into theta will be 1, 2, 1, 1, 3, 2, 1, 4, 4, 1, 1, 5, 1, 2, 6, 1, 3, 7 multiplied by 0, 0, 0. Now, if you know how to do matrix multiplication, the way to do this is first multiply the first row with this first column, then multiply the second row with the second column, and then do this for the 6 rows. So my final vector will have 6 rows and one column. So the way to think about this is that the first, this has 6 rows and 3 columns, right? And this has 3 rows and one column. So the final vector will always have 6 row and one column. So you have to take the first value from here and the last value from here to find the dimensions of the final vector. This is the trick which I use. Now since all of these quantities are 0, my x theta will look like zeros because everything is equal to 0. Correct? So the first quantity has been evaluated. It was quite simple. Now let me evaluate sigma of x of theta. This is the second quantity. So first quantity has been evaluated. Second quantity is taking the sigmoid. So sigma of x of theta means I have to take the sigmoid of 0, 0, 0, 0, 0, 0, which means that I have to take the sigmoid of every individual value. Sigmoid of 0. So there will be 6 values over here. Now, if you don't remember the sigmoid function, let me remind you what the graph for the sigmoid function looks like. It looks something like this. So it stagnates at 1. Uh, this is x and this is sigma of x. But the key thing to note is that at x equal to 0, sigma is not 0, but the value of sigma is 0.5. So that is the reason why after I apply the sigmoid function, sorry, I should say sigmoid, not sigma. After I apply the sigmoid function, since sigmoid of 0 is equal to 0.5, so the answer will be a vector of 6 values, each of which will be equal to zero point 0.5. Great. So I have calculated this third quantity, second quantity. Now let me subtract by y, which will be my third quantity. So my third quantity is sigma or sigmoid rather of x of theta minus y. And remember that the y vector we have already computed here. It is the vector of true labels. So then this value will be equal to zero point 0.5, zero point 0.5, zero point 0.5. We need to write it 6 times minus 1 1 1 0 0 0. That was my y value or the y vector. So this turns out to be minus zero point 0.5, minus zero point 0.5, minus zero point 0.5, zero point 0.5, zero point 0.5, and zero point 0.5. Great. So we have calculated this third. Now let us calculate the fourth value, which is this full thing, where in the fourth value, what we will do is that we will take an average. So 1 by n, so n is 6 since we have 6 points. So it will be 1 by 6 x transpose sigma x theta minus y. This we already calculated, this value in the third step. But x transpose. So if you know about the transpose operation, if our x is equal to this, if our capital X is equal to this, then X transpose, in X transpose just row will become columns and column will become row. So this vertical matrix will become an horizontal matrix. Think about rotating X anticlockwise. So X transpose will become this 1 1 1 1 1 1. So the column becomes the row 2 3 4 1 2 3 1 2 4 5 6 7. So here what I've done is that I've just taken this matrix and I've taken the transpose of it. So if you don't know matrix transpose, please look into it. It's a very simple concept. It's just rotating the matrix from vertical to horizontal in this case. And then this quantity we have already computed over here. It's minus zero point 0.5, minus zero point 0.5, minus zero point 0.5, zero point 0.5, zero point 0.5, and zero point 0.5. Now, so this is a three row six column, and this six row one column. So remember our trick, the final vector will be three rows and one column. So it turns out when you compute this thing, and I really encourage all of you to do it on your own, this turns out to be to have these values and 0.9167. After this is computed, this is the fourth step, then we have to do the final step, which is the simplest of all. It is just subtracting, it is just updating the theta. So in the final step, my theta 2 will be theta 1 minus alpha times the gradient which I computed above. And the alpha value which I'm going to use, which is also the one which I use in the code, is 0.01. This is a safe alpha to start with. So then my updated theta will be equal to 0.00, which was my earlier theta, minus 0.01 multiplied by this gradient which I calculated over here, is equal to 0, point minus 0.25 and 0.9167. So it turns out that the second theta value for me is 0, 0.0025 and minus 0.009167. This is the second iteration. This is the theta which I will obtain in the second iteration. Now, this is the same procedure which continues. These five quantities which are computed, right? 1, 2, 3, 4, 5. This is the same procedure for updating to theta 3. Same procedure for going to theta 4, then going to theta 5, then going to theta 6. That's it. This is exactly how the logistic regression algorithm actually works in practice. So if you look at the scikit-learn Python package, it has an inbuilt logistic regression library. And when you use that, you do not understand how that library is working. But this is exactly what is happening behind the surface or underneath the hood. It is essentially computing multiple of these iterations step by step. So right now we did the first iteration and I showed you how theta can be updated. This same 5-step procedure, these 5 quantities which you computed, is done for every single iteration. Sometimes 10 iterations might be needed, sometimes 100, sometimes 1000. Okay. I deliberately wanted to show you this before going to the code, because now that you understand this, understanding the code will be so much easier, because it exactly follows what we have written here. But if you directly jump into the code without understanding the basics, the fundamentals always remain unclear. Now let us take this particular demo which we have seen, and let us jump into Python code. Okay, so Python code for this project is very small, and I'm going to show you how different steps which we have written on the whiteboard translate to the code in Python as well. Uh, if I go some faster during the code, please let me know in the comments so that I can address each issue. But I don't want this to be a coding exercise. I really want for you to see how what we have written here very easily translates into code. When I give the code file to you, you can run it yourself, and when you run, that's when you will really understand it. So I highly encourage you to run the code files which I'm giving to you. Okay, so the code is very simple. The first thing to do is define the sigmoid function. So first of all, two libraries are needed: NumPy for scientific computation and Matplotlib for plotting. You have to import those two libraries initially. Then we have to define the sigmoid function. So the sigmoid function is just we have to use it at multiple places such as here. So it makes sense to define it at the start. It looks something like this from what we already saw in the plot. So the sigmoid function is just 1 upon 1 plus e raised to minus z that has been defined. The next thing what you do is you define the loss function. And remember what we saw about the loss function over here. The loss function is just this. The loss function takes in the hypothesis and the true value, the guess and the actual, and then this is how we compute the cross entropy loss. Y into log plus 1 minus y into log of 1 minus hypothesis, and take the negative of that. This is exactly what is written here. The reason why a mean is written is because when we compute the loss, we have to take 1 by n, right? So that's why the mean is written over there. This 1 by n. Okay. The second thing which we need to define is the gradient. And let us look at, so we already saw how the gradient looks like in matrix form. Look at this. This is how the gradient looks like, right? This is what we saw the gradient looks like in matrix form. This, this quantity which has been highlighted in pink. So it takes x which is converted to a matrix, sigma of x theta minus y. Now let us see the code. In the code, np dot x dot t, which is x transpose, which is this x transpose, correct? This has been written, and hx minus y. Hx is just taking the sigma of x theta. So hx has been defined later. If you see, hx is just taking a sigmoid of z, and z is just x theta. I'll come to it, no need to worry. But remember that this hx minus y is exactly what we had written here in sigma of x theta minus y, uh, and divided by y dot shape 0, which actually calculates the number of data points which we have. So actually, if you see, if you have understood this matrix form, right, the gradient and the way it is defined in Python is actually exactly similar to the way we have written it down on the whiteboard. Once we define the loss function, gradient and sigmoid, we are actually ready to run the full code. So first what we do is plot the data points. So as I mentioned, the data points look something like this, and we have already seen in detail what the data points look like here, the three positive and the three negative points. Correct. So first we plot the data. You don't need to do this. I just did this for demonstration purposes. And then we write the logistic regression algorithm itself. This is the most important piece of the code. So let me explain it to you step by step. So see, the first thing what they have also done is that they have taken our original x and augmented one to it. They have added one to it. They have added one more column. And the way they comment it out here, or with I have commented it out here, is add intercept term to x. So this part of the code is exactly similar to taking our x, which looked like these values, and converting it into this kind of an augmented into this augmentation matrix where you add a column of ones. This is exactly what is done in this function np.h stack, which means horizontally stacking them. So you horizontally stack this first column of ones with the other data points. That is what's done here. Then initialize the weights to zeros, which actually means that uh, theta initial is equal to 0 0 0. That's it. Then see what has been written. Then we are computing the gradient. So first we define hx as sigma of z. So hx will be sigma of theta. So remember, see what z is. Z is capital X into theta. So h of x is sigma of x theta. So sigma of x theta we have already defined here. See. So this step 2, this thing is actually h of x, what is written in the code. So this hx which is written is just this value sigma or sigmoid computed on x theta, correct? And then what do we do with this hx? We subtract y from it, right? This is very similar to what is done in the code also. So they have defined a compute, or we have defined a compute loss function over here. And if you see the compute loss, yeah, correct. This is how the loss function is computed. Um, and then we just take the gradient, and we have already seen it in compute gradient, this thing where we subtract y from hx. So we subtract y from hx and we take a dot product of x transpose and this quantity. This is exactly what we have done here. We subtract y from hx and then we take the dot product between x and this quantity in the fourth step. So I deliberately showed you this step so that when you go through the code, right, it is exactly similar to what we wrote down on the whiteboard. So when you reach this particular step in the code, gradient is equal to compute gradient. This just implements this gradient calculation which we have done in step number 4. And when the gradients are computed, we just do the step number 5. So step number 5 is updating the weights based on the current gradient value and the learning rate. So here you can see the weights are being updated. That's it. This is the code. You don't need to worry about plotting the decision boundary. I have just done it for purposes of this demonstration. But if you understand what is written on the whiteboard, you can see that the Python code becomes so much easier to understand. If you understand these 5 steps which we did over here, right? These 5 steps, uh, step number 1, 2, 3, 4, and 5. So let me maximize it a bit. Yeah, step number 1, 2, 3, 4, and 5. This part of the code, this part of the code is just doing these 5 steps. And then in the last line, we just implement logistic regression by taking the input x and the true values, which will just run this particular function. So this is the Python code for implementing logistic regression. And I encourage you to copy this code which I've shared with you and execute it on your own so that you become confident with it. Now let me execute it and show you how the decision boundary proceeds. So I'm doing 10 iterations right now, okay? So let me run this command for 10 iterations. Okay, so it's still running and now it's done. So look at this decision boundary. So this is after the first iteration, and look at the theta. The theta is 0, 0.0025 and minus 0.00916667. Do these numbers mean anything to you? We have already computed these exact same numbers here. See, these are the exact same numbers which we have computed here. Isn't this amazing? What we did using mathematics is the same thing which the computer does so quickly. So 0.0025 and minus 0.009167. These are the same numbers which you computed in the first iteration. But you see, it looks very bad. It does not classify the data correctly. In fact, the second iteration, the third iteration, the fourth iteration, you see the loss function is decreasing by a very low amount, 0.65, 0.64, 0.64, 0.63. So the classifier is getting better slowly, but still at the 10th iteration, we are not at a good classifier, which means we might need to increase the number of iterations. So let me try playing around with 100 iterations right now. And I won't plot everything for 100. So I will say that if, uh, so I want to say that if the iteration, if I percentage of 10 equal to 0, which means that I want to plot this at every 10th, I want to plot it at every 10th iteration. Okay, let me see if this works. So now I'm doing 100 iterations here, and I'm going to plot the decision boundary for uh, after every 10th iteration. So here you can see that this is iteration 20, it is getting a bit better. Iteration 30, it is getting definitely better. At iteration 50, it is much better. And here you can see that at iteration number 70, it classifies the data set perfectly, and after which it does not change. So it takes 70 iterations for our gradient descent algorithm to actually separate the data points perfectly. So we cannot do all of this mathematically, and that's why Python is used a lot. So we took 70 iterations. And the reason we took so many iterations, you might think, is probably because of the learning rate, right? So you can play around with this. Let's say I increase the learning rate by a factor of 10 times, and I still do 10 iterations, and I plot after every iteration. Let us see how this happens. So here I am exploring with the learning rate a bit. So now the learning rate has been increased 10 times, and here you can see that just within 6 iterations I am able to get to the perfect answer. This is the importance of a learning rate in gradient descent, and this is why you should have a keen understanding of what learning rate is. In the previous demonstration, the learning rate was very small, right? So it took a very long amount of iterations for the straight line to come at the correct answer. But now we increased the learning rate 10 times, and we obtained the correct answer in just 6 to 7 iterations. uh, Increasing the learning rate would not work always. If you increase the learning rate to more, let's say if I increase the learning rate to 100, let us see what happens. So here I am increasing the learning rate to 100, and let us see the plots. Here you can see that runtime error is there. So usually increasing the learning rate to too high of a value, so let me put it as 1 right now. um, or rather let me put it as 5. So generally increasing learning rate to too high of a value does not lead to quick convergence, and if you have it too low, then it leads to very slow convergence. So here you can see I have learning rate equal to 5, and again I have run into some error. But actually at iteration 3 it converges perfectly. So it just took 3 iterations with the learning rate 5 to converge. In some cases, if you increase the learning rate, the loss function will just keep on oscillating and never converge. So learning rate is a hyperparameter because you have to define it earlier. It's not a parameter, so it does not change while the iterations are proceeding. So that is the importance of learning rate. It's very important. So let me again dial it back what it was before. Uh, Learning rate of 0.01. Okay. I'll be sharing this code file with you. Please explore and try to experiment with several different values of learning rate, number of iterations, etc. So, thank you everyone. This brings us to the end of the lecture on logistic regression. I wanted to show you everything from scratch. So, we went into the fundamentals, we went into the foundation, and mathematically, we wrote down how the iterations look like. We also saw the importance of matrices and how they really simplify things in machine learning. Now hopefully you understand the importance of converting machine learning into an optimization problem, which we have looked at before. It just makes it easy because people have done optimization problems a lot before. They know how to minimize or how to do gradient descent. So essentially we convert the ML problem into an optimization problem. But whenever you go for job interviews, please make sure that your fundamentals are clear. Don't just run Python scripts. In fact, uh, scikit-learn now provides everything out of the box. So scikit-learn, if you type scikit-learn logistic regression, it just directly provides this function. So when you do this in one line, you will get this entire code. You won't even know what the derivatives are. You won't even know what the loss function is, etc. What we have done today is dig deeper and understand how these functions work. Many engineers just load these packages and apply these packages. That's why their fundamentals are not strong. I think it's very important to build strong fundamentals while also have hands-on practical knowledge. So I really encourage everyone to run these codes and write down this derivation on your notebook with pen and paper. Do this for the one point of iteration and see how the learning rate or how the theta changes. You will never forget logistic regression after this. Thank you so much, everyone, and we'll be covering many such topics in extreme detail as we have done with this one. I'll see you in the next lecture.